a nonlinear map over here, and we know through some flash of divine insight, or perhaps through some off-screen calculations, that the fixed points here are the origin and minus 0.6, minus 0.6. The question is, what about the stability of these fixed points? So pause the video for the calculations. First thing we need to do, obviously, is calculating the Jacobian. So the Jacobian is a matrix consisting of all the different partial derivatives here, which we denote by df. Now the first row in this matrix is all about the partial derivatives of the first function, so minus x squared plus 0.4y. So taking these partial derivatives gives us minus 2x for the partial derivative with respect to x, and then a constant 0.4 for the partial derivative with respect to y. For the second row in our matrix, we take a look at that function over here, which is just a boring x, and the partial derivatives reduce to 1 and 0. Okay, that's the first step. Next step is evaluating that Jacobian in the points of interest. So the first point of interest is, of course, the origin. If we plug in 0 everywhere, we get a matrix 0, 0.4, 1, and 0. Now this is a map which corresponds to a linear approximation of our nonlinear map. And in order to look at the stability of this thing, again, we need to calculate the eigenvalues. That's rather straightforward in this case. Our determinant looks quite simple. So this thing needs to be equal to 0, or lambda squared minus 0.4 should be equal to 0. You can quickly see that the magnitude of these eigenvalues, they're all smaller than 1. So this is a stable fixed point or a sink. Okay, next step is doing the same thing, but for the different fixed point. In case you haven't done so, I pause the video here to give you a chance to do just that. Moving on, for the second fixed point, our Jacobian evaluated at a point minus 0.6, minus 0.6 looks slightly more complicated. So we have minus 2 times the x value. So this is going to be 1.2, and otherwise still 0.4, 1, and 0. So that is our linear map approximating the nonlinear map at a fixed point. The eigenvalues are calculated using the following determinant. This thing equal to 0, which means that we have minus 1.2 lambda plus lambda squared minus 0.4 equal to 0, or lambda squared minus 6/5 of lambda minus 2/5 equal to 0. Cleaning this thing up a little bit, 5 lambda squared minus 6 lambda minus 2 equal to 0. It's no big deal to calculate the eigenvalues. So again, we have an even factor b here, so we can use the reduced formulas, so using half of the coefficient of lambda plus or minus, and then the square of this 3 minus the product of the first and the last coefficient. So this gives us plus 2 times 5, 10, divided by the coefficient of lambda squared. So these are our 2 eigenvalues. If you take a calculator, you will quickly be able to calculate that the first one is roughly 1.47 and the second one is minus 0.27. The important part here is that one of those is in magnitude bigger than 1 and the other one is in magnitude smaller than 1. So one attracting direction, one repelling direction. that is of course a saddle point here. So the second fixed point is a saddle.